I am the Philosophical Bachelor. My aim in this series is to examine Charles Sanders Peirce's Metaphysics and to do so based on his 5 articles in the Monist. However, I realized that Design and Chance, a lecture Peirce delivered to the Metaphysical Club at Johns Hopkins University in 1884, is helpful as a supplement to his first Monist paper, The Architecture of Theories, and so I decided to look at it also. Design and Chance is written about 7 years before The Architecture of Theories. It shows the trajectory of Peirce's thoughts when he was developing his metaphysics and how consistent it was. It also offers clarity to his Monist papers. The state of human knowledge at any point in time is determined by what came before that led to its current state. We can only build on, react to, reform, or discard and replace the knowledge we already have. Peirce believes that the time has come to question the exact truth of axioms. He is referring to axioms in general, but geometry is the example par excellence to demonstrate just how shaky the foundations of knowledge really are. Peirce is writing for an academic audience and so does not bother to go over ground well known to his fellow mathematicians and thinkers. I cannot presume you, my listeners, are of the same ilk as them, and so a brief excursion of just what the big deal is about is in order. Euclid wrote Elements around 300 BC, which formed the basis of our knowledge of geometry up until the early 19th century. The Euclidean axioms are: 1. Given 2 points, there is a straight line that joins them. 2. A straight line segment can be prolonged indefinitely. 3. A circle can be constructed when a point for its center and a distance for its radius are given. 4. All right angles are equal. 5. If a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, will meet on that side on which the angles are less than the 2 right angles. Axioms are propositions that are given, usually considered self-evident, and are so fundamental that it is not possible to prove them. If you think through the Euclidean axioms, you can understand why. How exactly is one meant to prove that for any 2 points there exists a straight line that connects them, or that all right angles are equal to one another? You may realize yourself that not everything can be proved. Proofs depend on more fundamental propositions that have been proved, and as we go down the series of more and more fundamental propositions, we finally get to propositions that cannot be proved because they are the most fundamental. These are known as axioms. Axioms are what proofs for all other propositions are built on. They themselves cannot be proved because they are ground zero or rock bottom. There is nothing more basic than them on which their proofs can be built on. Hence, they have to be assumed to be true. So Euclid's axioms stood for over 2,000 years before they were successfully called into question in the early 19th century, specifically the 5th axiom, also known as the parallel postulate. Simply stated, it tells us that parallel lines do not converge. 3 mathematicians, Nikolai Lobachevsky in 1829, Janos Bolyai in 1832, and Carl F. Gauss, who wrote but did not publish his findings for fear of ridicule, realized that a consistent geometry can be developed assuming the 5th axiom is false, that parallel lines do converge. Euclid's geometry works for planes, but not in curved spaces or spheres. In a planar space, parallel lines indeed do not converge, but they do in curved and spherical spaces. From there, we get hyperbolic and spherical geometry respectively, which are forms of non-Euclidean geometry. Recall that Peirce was born in 1839 and was mathematically minded. Talk about the right place at the right time. He thought it was ripe to question the truth of axioms in general because the exactness and truth of the axioms of geometry have been called into question with non-Euclidean geometry. If something that was relied on and considered true and unchallenged over thousands of years can be challenged so successfully, why not other axioms? You know how it is said that there is a time and place for everything? This idea is from the Bible. For everything there is a season and a time for every matter under heaven. Peirce thinks that there is a time for insisting on the exactitude of established laws. When science was still at a nascent stage, to question the exactitude of established laws can only lead to confusion. However, there comes a time when it is appropriate to do so, and that time is when we are in possession of a guiding idea which shows us in what manner they may possibly be corrected. Recall that Peirce is the founder of pragmatism. If one has no solution to a problem, then all one has is criticism. However, if one has at least an inkling of how a problem can be solved, then there is at least a starting point from which a new system can be built. His claim is modest. We do not say that the laws of nature is likely to be inexact. Far from it. We only say that the question whether it is exact or not has come to have a claim to consideration greater than it had in a former state of science, he writes. And what better place to start with than geometry, which for millennia have been considered exact and hence not in question. It is not merely that some mathematicians have developed alternative geometries to Euclid's. One result of Euclid's geometry is that the angles of a triangle add up to 180 degrees. This can be verified empirically. The angles of a triangle were measured on an astronomical scale, using the Earth's orbit as the base and the stars as apexes. Results have shown that indeed some stars give the sum of the angles as differing from 180 degrees. So even axioms from the sciences that were considered solid have been shown to be not so certain. Logic is Peirce's pet subject matter. He wanted to be a logician when young, but was dissuaded by his father, a professor of mathematics at Harvard University, who told him it was untenable since no one could make a living as a logician at that time. Logic, like Euclidean geometry, was another system thought to be irrefutable. One axiom from logic, or simply from our common understanding of the world, is that every event has a cause. What earlier thinkers like Gottfried Wilhelm Leibniz called the principle of sufficient reason. Could some events have no cause if we had better instruments to measure cause and effect, or if we simply waited long enough for aberrations to arise? May it not be that chance, in the Aristotelian sense, mere absence of cause, has to be admitted as having some slight place in the universe, asked Peirce. This chance in the Aristotelian sense must be noted. He is not referring to an ignorance of causes such that we call an unexplained event chance. He is speaking of true chance, where things happen randomly in a way not attributable to any cause, not because we are ignorant of its cause, but because there is no cause. It happened truly by chance. The way a flip of a coin or a toss of the dice in perfectly ideal conditions cannot be predicted with certainty beforehand. If the principle of sufficient reason holds that every event has a cause, then every fact has an explanation, a reason. It also means that every single law of science, of nature, should be explainable. And then the general fact that there are laws, how is that to be explained, he adds. How can we account for the fact that laws of nature even exist, that the universe is orderly enough that we can discover how it works and describe these workings using laws? Why is the universe orderly in the first place? Peirce's answer to these questions is an appeal to chance plus evolution. He thinks that the notion of evolution is built into the fabric of logic itself, though logic has not been understood as such. Evolution is the postulate of logic itself. For what is an explanation but the adoption of a simpler supposition to account for a more complex state of things, he writes. What is evolution in biology? It is a theory of how simpler living things become more complex living things. How, for instance, human beings, a more complex animal, evolved from more primitive and simpler ancestors. What is logic and the logic of explanation? Is the adoption of simpler suppositions to account for a more complex state of things, the paradigmatic example being geometry, which builds from simple axioms to more complicated theorems. His point is, this movement from simple to complex is precisely what evolution is, and evolution applies not only to biology, but even in logic. When thinkers such as Darwin theorize about evolution, however, they make an implicit assumption that the laws of nature has been the same from the start and will remain the same in the future, that the laws of nature are eternally unchanged. And herein lies the thunderbolt idea that Peirce was building towards in his lecture, a theory of the evolution of physical law. We understand laws to be unchanging. Indeed, it is why laws are even called laws. They are supposed to be a form of eternal and hence absolute truth. But Peirce is calling that into doubt. However, he has a solution to propose, and that solution is the role of chance. In fact, chance is going to save the principle of sufficient reason. The hypothesis of absolute chance is part and parcel of the hypothesis that everything is explicable, not absolutely, rigidly, without the smallest inexactitude or sporadic exception, for that is a self-contradictory supposition, but yet explicable in a general way, he writes. The principle of sufficient reason is contradictory or rather contradicted, since exceptions have been observed. But it is self-contradictory, because if we admit it, how do we explain why everything is explicable? Peirce is here questioning the validity of the axiom of the principle of sufficient reason, or at least its exactness. It states that every cause has an effect, which is tantamount to everything being explicable, but how does it explain itself without asserting itself, hence making a circular argument? If, however, we admit that chance has a role, then indeed everything is explicable, albeit in a general way. So how do laws evolve to be the fixed and precise propositions that we understand them to be? Peirce illustrates how it happened by way of a thought experiment. We have a fair dice with 1 million gamblers with $1 billion. Over 1 million bets, the statistical distribution of the result is well defined. It is a curious and apparently paradoxical result that although everything is supposed to happen by pure chance, yet we know very closely how those million players will stand at the end of 1 million bets, he observes. It is the law of large numbers. Statistical outcomes of games of chance, such as dice, are calculable, and while the winnings of any specific player is not known through statistics alone, the distribution of winnings across the population is known. Chance has been playing a role, but a role we understand well enough to mathematically describe the broad outcomes. But the story does not end there, and indeed, what Peirce is about to do next more resembles what may possibly happen than the story so far. Suppose that the dice used by the players become worn down in the course of time. Chance changes everything, and chance will change that, he writes. Indeed, over 1 million tosses, the dice may be worse for wear, and casinos know this, which is why they change to new dice long before 1 million tosses. In the thought experiment, Peirce also asks us to assume the way that the dice wears is such that it will continue wearing in the same direction, such that it biases the result to, for instance, the larger numbers. He does not say this, but for simplicity's sake, let us also assume that this game is big-small, or 大小, a Chinese game of dice where you bet either on the big numbers of 4, 5, and 6, or small ones of 1, 2, and 3 to come up. This is why I prefer using a coin toss in my previous essay. It is simpler to explain. And let us say that the players always bet the same way, so once player A bets small, she continues betting small as long as she is in the game. This small bias of a wear to one side favoring big will over many games separate the players into two classes of winners and losers, with few staying the same. Naturally, the more worn or biased the dice, the faster the separation. And the dice over time, since it is tossed small, wears small, accelerating the separation. Generalizing the separation, those with bad habits are destroyed, while those with good ones are preserved, hence increasing the average strength of the survivors. Remember, Peirce is a pragmatist, so what he means by bad and good is a pragmatic bad or good, where bad is what one does habitually leading to disadvantageous outcomes, while good is what one does habitually that gives advantage. He is not making a moral judgment. Chance could of course act in other ways, for instance wearing to one side biasing big in one round and then wearing to another biasing small in another, such that it remains fair. Indeed, how chance will act is a matter of chance, and the way chance acts is inexorable. Say somehow it favors in our scenario one particular player, let's call her Jamie. Even if Jamie is taken off the table, someone else will simply take her place as being the lucky player, leaving the ultimate result unchanged. Force is in the long run dissipative. Chance is in the long run concentrative, according to Peirce, causing a balance between the opposing tendencies to leave us where we stand now. Laws that are probabilistic, statistical, such as the gas laws from Charles and Boyle, describe the overall movement of a multitude of molecules. But even putting aside such laws based on molecular movement in the kinetic theory of gases, laws of Newtonian mechanics, and in fact all laws of nature, are statistical results in Peirce's view. He writes, "All known laws are due to chance and repose upon others far less rigid themselves due to chance, and so on in an infinite regress. The further we go back, the more indefinite being the nature of the laws, and in this way we see the possibility of an indefinite approximation towards a complete explanation of nature. Chance is indeterminacy, is freedom, but the action of freedom issues in the strictest rule of law. In the beginning there was only chaos, only chance. Then by pure chance a bias in the randomness arises, which then becomes increasingly biased over time to finally produce a strict outcome. The way our dice, as it becomes increasingly worn, may finally always end up coming up big." Let's take a law of mechanics as an example, the second law of Newton's mechanics, which gives force equals to mass times acceleration. Today, the outcome of the product of mass and its acceleration strictly gives us the force involved. According to Peirce's theory, the further back in time we go, the less strict this relation was. This idea deviates from how we understand scientific laws today, but precisely therein lies its genius. Peirce gives us a way of explaining how from total freedom in the form of randomness can come the strictest laws. What if behavior of certain substances differ by chance? Say there are rocks that float and rocks that sink in air. Today we observe only rocks that sink because those that float would already have floated into space, leaving us only the rocks that sink. So we can see how laws of nature in this case can evolve from one describing a more indeterminate sinking and floating to just what appears to be a completely determinate sinking under the influence of gravity. Thank you for listening to the Philosophical Bachelor.